Hello, Namaste, and welcome everyone. My name is Piyush Tiwari, and today I will be presenting our work titled Minority Oversampling for Imbalanced Data via Class-Preserving Regularized Auto-Encoders. This work is jointly done by people from IIT Delhi and IISc Bangalore. The broad issue that we try to tackle in this work is that of class imbalance in datasets, which is very ubiquitous in several settings, such as fraud detection and clinical anomaly detection. Further, class imbalance also leads to several issues in machine learning, like that of overfitting and manifestation of undesired biases in models. To overcome this issue of class imbalance, there have been two broad categories of solution. The first one is that of data resampling, where we try to get rid of the imbalance in data either by undersampling or by oversampling. And the second category is that of cost sensitive methods, where we try to bias the gradients to take into account the minority class by reweighting the loss terms. This work in particular falls under the category of data resampling methods. There are two possible ways to overcome class imbalance via resampling. The first approach is that of undersampling, where we reduce the number of samples in the majority class to match the number of samples in the minority class. And the second approach is that of oversampling, where we do the opposite of undersampling and try to sample more points from the minority class to match the size of majority class. There have been several works in this area of oversampling. For example, traditional methods like SMOT and ADASIN try to interpolate between minority data points to sample more points. Similarly, there have also been some deep learning based approaches such as PA-GAN, GAMO, and DeepSmart. Given these methods, we ask ourselves as to what are the properties that a method should inherit in order to be a good oversampling method. We conjecture for four such properties. In particular, the oversampling should occur in a low dimensional space. The second conjecture is that the oversampling procedure should be independent of explicit distance metric. And third conjecture is that the oversampling procedure should ensure that class is preserved while oversampling. And the last conjecture is that it should learn to oversample while learning the decision boundary. Previous SOTA methods miss out on one or more of these properties, while our method ensures that all of these properties are satisfied simultaneously. So this is the overview block diagram of the proposed method. Firstly, the input is passed through an encoder network to get low dimensional representation of inputs Z1 to Zn. These vectors are passed through a mixer network, which is nothing but a simple feed-forward network to generate mixing coefficients, alpha 1 to alpha n. Here we ensure that summation alpha is 1 and each of the alpha is lie between 0 and 1. So that when we take the convex combination of zi's using alpha i's, we get z dash. Then the original embedding zi's and z dash are passed through the linear classifier LW, and the class of z dash is fixed to be the same as that of zi's. Further, we also use a decoder d theta to ensure that z dash corresponds to a visually similar looking image as that of inputs. Now for the proposed method, we are able to provide several theoretical guarantees. The most important of which is the following, which says that if two classes are linearly separable, then any data point sampled from the convex hull of a particular class preserves the class. This is quite easy to prove. Nonetheless, it forms the backbone of our method. Next, we can also show that if we choose the appropriate mixing coefficients, then the variance of the empirical risk obtained using our method will be smaller than that obtained using the naive methods. Now, using this previous result, we can directly provide a pack bound on the empirical risk using straightforward concentration inequalities. Further, we also show that under our setting, one can obtain a linear classifier whose Lipschitz constant is upper bounded, which reduces the chances of overfitting. Moving to the experimental results, Here we can see the performance of our method relative to the previous SOTA methods. And we can see that the proposed method beats other methods by significant margin. To end with, we have proposed a oversampling strategy that ensures class preservation. In addition to this, we also have several theoretical guarantees for the proposed method. We conclude with the remark that in real world, there might be several additional constraints such as fairness and privacy constraints. Moreover, deploying the proposed method further warrants for rigorous and validation for high-stake applications. With this, I would like to conclude the presentation. Thank you and have a nice day.